Welcome to today's problem walkthrough. We'll be solving problem number 1397, titled Find All Good Strings. In this session, we'll explore the problem's requirements, consider different approaches, and ultimately land on an optimal solution. Let's dive in. In this problem, we are tasked with finding the number of strings, called good strings, that meet two specific criteria. First, the string must lie lexicographically between two given strings, S1 and S2, inclusive. This means the string should be greater than or equal to S1 and less than or equal to S2. Second, the string must not contain a given substring, evil. The result should be returned as an integer modulo 10 to the power of 9 plus 7. The input consists of three strings, S1 and S2, both of length n, and evil, of length m. The output is a single integer representing the count of all good strings that satisfy these conditions. To better understand the problem, let's look at examples. For the first example, we are given S1 as AA, S2 as D, and evil as B. When we list all strings between S1 and S2 lexicographically, we get strings like AA, AB, AC, and so on, up to D. In total, there are 104 such strings. Among these, we need to exclude those that contain the substring B. After filtering out the invalid strings, we are left with 51 good strings that do not contain B. Therefore, the output is 51. In the second example, S1 is AAA, S2 is ABC, and evil is C. The lexicographical range here includes strings such as AAA, AB, AAC, and so on, up to ABC. Among all these strings, 460 of them do not contain the substring C. Hence, the output for this case is 460. Similarly, for the third example, where S1 is A, S2 is Z, and evil is Z, the range includes all single character strings from A to Z. Excluding Z, which contains the substring Z, we are left with 25 good strings. The output here is 25. To summarize, the constraints of the problem define additional considerations. The lengths of S1 and S2 are equal, denoted as n, and can go up to 500. The length of evil, denoted as m, can go up to 50. Both S1 and S2 consist of lowercase English letters, and evil also consists of lowercase English letters. Additionally, S1 is guaranteed to be lexicographically less than or equal to S2. It's important to account for edge cases, such as when S1 and S2 are the same, which means the result depends solely on whether evil appears in S1. If evil is empty, all strings in the range are valid, and if n or m are near their upper limits, the solution must handle these efficiently. To solve this problem efficiently, we need techniques that address the constraints of large string lengths and the substring detection. Dynamic programming is a key approach here, as it allows us to systematically count valid strings while avoiding those that contain evil. Furthermore, combining this with string matching algorithms, like the Knuth-Morris-Pratt (KMP) algorithm, can help optimize the detection of evil within candidate strings. These techniques are essential for ensuring the solution performs well within the given limits and produces results accurately and quickly. To begin, let's consider the brute force approach to solving this problem. The idea here is to generate all possible strings that lie lexicographically between S1 and S2, and then filter out the ones that contain the substring evil. This involves iterating through every string in this range, checking each one for the presence of evil, and counting only the valid strings. While this approach is conceptually simple, it becomes computationally infeasible as the size of the input grows. The reason is that the total number of strings grows exponentially with the length of S1 and S2. For instance, if the strings have a length of n, even with a relatively small alphabet, the number of possibilities could approach 26 to the power of n. Additionally, searching for the substring evil in each candidate string adds even more computational overhead. This makes the brute force method impractical for solving the problem efficiently, particularly when the input constraints are large. To address the inefficiencies of the brute force approach, we turn to a more optimized solution using dynamic programming combined with the Knuth-Morris-Pratt (KMP) algorithm. The core idea is to build valid strings one character at a time, ensuring that the constraints S1 equals X equals S2 and avoiding the substring evil are maintained throughout. The KMP prefix function is especially helpful here, as it allows us to efficiently track how close the current string is to matching the evil substring. By treating this as a state machine, we avoid the need to explicitly check for evil at each step. Additionally, the lexicographical constraints can be dynamically managed by tracking whether the current prefix is still tightly bound by S1 or S2. This decomposition into smaller, overlapping subproblems is what makes the dynamic programming approach suitable. To formalize this, we define a DP state, DP, POS, K, tight underscore lower, tight underscore upper, where POS represents the current position in the string, K tracks the state of the KMP automaton, and the two tight flags indicate whether the current prefix is still constrained by S1 or S2. This setup allows us to systematically explore all valid possibilities while respecting the problem's constraints. The dynamic programming solution involves transitioning between states based on the character being added at each position. For every character in the alphabet, we update the KMP state to reflect whether the new character moves us closer to matching the evil substring. At the same time, we check if adding the character keeps the current string within the bounds defined by S1 and S2. By accumulating the results for all valid transitions, we can efficiently count the total number of valid strings. The base case for the DP occurs when we have processed all positions in the string. At this point, if the string is valid, meaning it does not match evil and lies within the bounds, we return 1. Otherwise, we return 0. The time complexity of this approach is O(n*m*4 by 26, where n is the length of S1 and S2, m is the length of evil, and 26 represents the alphabet size. The space complexity is similarly optimized at O(n*m*4). This efficiency comes from avoiding explicit string generation and leveraging the structure of the problem to systematically explore the solution space. While the implementation is more complex than brute force, it is scalable and practical for large input sizes. There are alternative approaches to solving this problem, though they are generally less efficient than the DPKMP strategy. For example, a tree-based approach could be used to build a tree structure of all valid strings, pruning branches that contain the evil substring. However, this method struggles with efficiency for large alphabets or long string lengths. Recursive backtracking is another option, which can be combined with memoization to reduce redundant computations. However, it lacks the structured optimization provided by dynamic programming and is harder to optimize for complex constraints. Ultimately, the DPKMP approach is the chosen strategy due to its ability to leverage the problem's structure for both correctness and performance. By combining dynamic programming with the KMP algorithm, we can efficiently count valid strings without explicitly enumerating them. This ensures the solution remains scalable even for large constraints, making it the most practical and robust choice for this problem. To solve this problem, we are tasked with finding all strings between two given lexicographically sorted strings, S1 and S2, that do not contain a forbidden substring called evil. Instead of generating all possible strings, which would be computationally expensive, our goal is to count these valid strings efficiently. The key to this lies in breaking the problem into manageable subproblems using dynamic programming. To do this, we need to think in terms of states. Each valid string must lie between S1 and S2 in lexicographical order. At any given position in the string being formed, we must consider three main factors: the prefix of the string we've built so far, whether this prefix matches part of the evil substring, and whether the string remains tightly bounded by S1 and S2. These observations form the foundation of the algorithm. To represent this problem with dynamic programming, we define the state DP, POS, match, tight 1, tight 2. Here, POS represents the current position in the string being constructed. The match variable tracks how much of the evil substring has been matched so far. The tight 1 and tight 2 flags indicate whether the current string prefix is still tightly bounded by S1 and S2, respectively. For transitions between states, we iterate over all possible characters from A to Z at each position. For each character, we update the match state based on whether the new character extends the match of the evil substring. If the match reaches the full length of evil, this branch is invalid and contributes nothing to the count. We also update the tight 1 and tight 2 flags to reflect whether the new prefix remains within the bounds of S1 and S2. These transitions allow us to build valid strings incrementally while ensuring the constraints are met. Finally, when we reach the base case where the string length equals S1 or S2, we check whether the evil substring has been matched. If not, this represents a valid string, and we return one for it. To begin solving the problem, we initialize the dynamic programming process with the state DP 0, 0, 1, 1. This corresponds to starting at the first position of the string, with no prefix of the evil substring matched yet, and with the string tightly bounded by S1 and S2. From this initial state, we compute the result recursively with memoization or iteratively using a bottom-up approach. As we explore all possible states, we sum the contributions from all valid end states to determine the total count of valid strings. Memoization ensures that we avoid redundant computations by storing results of previously computed states and reusing them when needed. This not only speeds up the algorithm but also ensures it can handle larger input sizes efficiently. The algorithm relies on several key insights to achieve efficiency. First, we avoid explicitly generating all strings within the range S1, S2, as this would be computationally prohibitive for large ranges. Instead, the dynamic programming approach focuses solely on valid transitions between states. Second, the match state allows us to track partial matches with the evil substring, enabling early termination of invalid branches. Third, the Type 1 and Type 2 states enforce lexicographical constraints dynamically, ensuring that all generated prefixes remain within the bounds of S1 and S2. Finally, memoization is crucial for avoiding redundant computations, as many states may be revisited with the same parameters during the process. The DP table or memoization cache is structured to store results for each state, with a time complexity of O, n*m*26, and space complexity of O, n*m*2 by 2, where n is the length of S1 or S2 and m is the length of the evil substring. This careful use of states and optimizations ensures that the algorithm scales well to large inputs. Handling edge cases is an important part of ensuring the algorithm is robust. For instance, when S1 and S2 are the same string, the output is 1 if the evil substring is not present. If the evil substring is longer than S1 or S2, it can never appear, meaning all strings in the range are valid. In cases where evil is empty, all strings are valid, and the result is simply the size of the range. Additionally, if S1 or S2 contains invalid characters outside the range A to Z, input validation should handle these scenarios. In summary, this algorithm efficiently counts valid strings by combining dynamic programming, substring matching, and type bounds. By avoiding explicit generation of strings and leveraging state transitions and memoization, it ensures optimal performance even for large input sizes. Here, we start by importing the ru_cache decorator from the functools module, which will help us optimize our recursive function with memoization. Then, we define a class called solution and implement the main method findGoodStrings. This method takes 4 parameters, the length of the strings n, the 2 boundary strings S1 and S2, and the evil substring that we need to avoid. We also define a constant mod to store the value 10 to the power of 9 plus 7, which will be used for modular arithmetic to prevent overflow. Next, we implement the build_kmp function, which computes the kmp failure function for the given evil substring. This function generates the longest prefix-suffix array, or LPS, which helps us efficiently track matches of the evil substring during our recursive traversal. Inside the function, we initialize the LPS array with zeros and use a variable j to manage the prefix length. As we iterate over the pattern, we update the LPS array based on how much of the prefix matches the suffix, ensuring efficient backtracking if mismatches occur. Finally, we return the completed LPS array, which will be used later in our main logic. After building the LPS, we define the DP function, which is a recursive helper function decorated with ru_cache for memoization. This function takes 4 parameters, IDX, which tracks the current position in the string, prefix 1 and prefix 2, which indicate whether we are still adhering to the boundaries defined by S1 and S2, and matched, which tracks how many characters of the evil substring have been matched so far. Inside the DP function, we first handle 2 base cases. If the entire evil substring has been matched, we return 0 because this path is invalid. Conversely, if we have processed all n characters without fully matching evil, we return 1, as this represents a valid good string. Now, we define the range of characters that can be used at the current position IDX. This is determined by whether we are still constrained by the prefixes of S1 and S2. If prefix 1 is true, the starting character is the one at S1, IDX, otherwise, it's a. Similarly, the ending character is determined by prefix 2, defaulting to Z if there's no constraint. We initialize a variable total to accumulate the count of valid good strings for this position. Then, we iterate over all possible character codes within the defined range. For each character, we determine whether the new character maintains the prefix constraints by comparing it to S1 IDX and S2 IDX. If it matches the current boundary characters, the corresponding prefix flags, next underscore prefix 1 and next underscore prefix 2, remain true, otherwise, they are set to false. Next, we compute the next underscore matched value to determine how much of the evil substring matches if we include the current character. Using the LPS array, we efficiently backtrack to the longest valid prefix match when there's a mismatch. If the character aligns with the next character in the evil substring, we increment next underscore matched. Finally, we recursively call the DP function to process the next index with the updated constraints and matching status. The result is accumulated into total, and we ensure it stays within the mod limit to prevent overflow. After iterating through all possible characters, we return the total count of good strings for this state. At the end of the outermost function, we invoke DP starting with IDX0, both prefix flags set to true, and matched set to 0, representing the initial state of our computation. To solve the problem of finding all good strings, we start by setting up the Java implementation with a class-named solution. The constant mod is defined to handle large numbers using modular arithmetic, ensuring that the results remain within manageable limits. The main function, findGoodStrings, takes the length of the strings n, two boundary strings s1 and s2, and the forbidden substring evil. The first step in the solution involves pre-processing the evil string using the KMP algorithm to build its longest prefix suffix, LPS, array. The buildKMP function calculates this array, which helps in efficiently matching the evil substring during the dynamic programming process. The for loop iterates over the pattern, updating the LPS array based on previously computed values, ensuring that we can quickly backtrack when mismatches occur. This pre-processing is crucial for detecting and avoiding the evil substring as we generate valid strings between S1 and S2. The dynamic programming function DP is the core of our solution. It recursively calculates the number of valid strings that can be formed while respecting the constraints. The parameters include the current index IDX, two booleans prefix 1 and prefix 2 to track if the current string is still bounded by S1 and S2, the match length of the evil substring so far, and other necessary inputs like the LPS array and memoization table. The base cases are straightforward. If the evil substring is fully matched, we return 0 since the string is invalid. If we reach the end of the string without matching evil, we return 1 to count this valid string. Memoization is used to store previously computed results, avoiding redundant calculations. The loop iterates over possible character values for the current position, respecting bounds set by S1 and S2. Inside the loop, we calculate the next prefixes and determine how much of the evil substring is matched, updating these values dynamically to reflect the current character's impact. For each character value in the current range, the DP function is called recursively to explore the next index while updating the constraints and match state. The result of each recursive call is added to the total, which tracks the number of valid strings for the current state. Modular arithmetic is applied to ensure that the total remains within the specified limits. Finally, the computed value for the current state is stored in the memoization table to avoid redundant calculations in future calls. This process ensures that we efficiently explore all possible strings between S1 and S2 while avoiding any that contain the evil substring. The function ultimately combines dynamic programming with efficient string matching techniques to solve this problem within the given constraints, producing the total number of good strings modulo mod. To solve this problem, we start by initializing and pre-computing the KMP failure function for the evil string, which is B in this example. The KMP failure function, or LPS array, helps us efficiently determine partial matches of the evil string during our string generation process. Since B is a single character, its LPS array is simply 0. This indicates there are no proper prefixes that are also suffixes. Next, we set up our recursive dynamic programming function, DP. This function takes 4 parameters, IDX, which represents the current position in the string, prefix 1 and prefix 2, which track whether the generated string still respects the bounds defined by S1 and S2, and matched, which tracks how much of the evil string has been matched so far. Additionally, we use a modulo value, mod equals 10 to the power of 9 plus 7, to prevent overflow during computations as we accumulate results. Now, at the first position, idx equals 0, we determine the range of valid characters based on the prefix constraints. Since both prefix 1 and prefix 2 are initially set to true, the valid character range is the entire alphabet, from A to Z. Within this range, we loop through each character. For char equals A, it respects the lower bound defined by S1, so next underscore prefix 1 remains true. However, it exceeds the upper bound of S2, so next underscore prefix 2 becomes false. The next underscore matched value remains 0 because it does not match the evil string. We then recursively call dp for the next position. On the other hand, for char equals b, it does not respect the bounds of S1 or S2, so both next underscore prefix 1 and next underscore prefix 2 are set to false. Here, next underscore matched becomes 1 because b matches the evil string, and since we've matched the entire evil string, we terminate this branch and return 0 immediately. Moving to the second position, idx equals 1, we continue processing valid characters. For example, if the previous state led to dp, 1, true, false, 0, and we choose char equals A, the next underscore matched value remains 0, and we recursively call dp again for the next index. Once we reach idx equals 2, which is the base case, we return 1 because we've successfully generated a string of length 2 that avoids the evil string. With this process, the total number of valid strings of length 2 that avoid the evil string is calculated to be 650. Now, let's explore another example with a longer string. This time, n equals 3, s1 equals abc, s2 equals xyz, and evil equals bc. First, we precompute the KMP failure function, or LPS array, for the evil string bc. Since there are no repeating prefixes and suffixes in bc, the LPS array is 0, 0. This will help us efficiently track matches while generating strings. The recursive dp function is again initialized with idx equals 0, prefix 1 equals true, prefix 2 equals true, and matched equals 0. At this first position, the range of valid characters is A to X, because we're constrained by the bounds of S1 and S2. For char equals A, we recursively call dp, 1, true, false, 0, since this still respects the lower bound of S1, but no longer fits within the upper bound of S2. For char equals b, we update next underscore match to 1 because it matches the first character of evil, and we recursively call dp, 1, false, false, 1, to proceed. At the second position, idx equals 1, we continue processing valid characters. For instance, if we're in the state dp, 1, true, false, 0, and choose char equals b, the next underscore matched value is updated to 1, as b matches the first character of the evil string. We then recursively call dp, 2, false, false, 1, to process the next position. On the other hand, if we're in the state dp, 1, false, false, 1, and choose char equals c, the next underscore matched value becomes 2, indicating that the substring bc fully matches the evil string. At this point, we terminate this branch and return 0, as strings containing evil are not valid. After exploring all possibilities, the total number of valid strings of length 3 that avoid the evil string is calculated to be 456. To analyze the time complexity of our solution, we need to consider two major components: pre-processing the evil string and solving the problem using recursion with memoization. First, the pre-processing step involves building the KMP failure function for the evil string, which has a length of m. This step requires a single pass through the string, resulting in a time complexity of O(m). Next, we have the recursive function that computes the number of valid strings. This function depends on 4 parameters, idx, which ranges from 0 to n1, contributing in possible states, prefix 1 and prefix 2, which can each be true or false, giving 4 combinations, and matched, which tracks the number of characters matched in the evil string and ranges from 0 to m, resulting in m plus 1 possible values. Multiplying these dimensions, we find the total number of states in the memoization table is n*m. For each state in the recursive function, there is an additional step where we loop over all possible characters in the alphabet. Since the alphabet contains 26 characters, this adds a constant factor of 26 to each state. Combining this with the total number of states, the overall time complexity of the recursive function becomes n*m*26. However, since 26 is a constant, we simplify this to n*m. Moving on to space complexity, the pre-processing step with the KMP failure function requires an LPS array proportional to the length of the evil string, which is O(m). Additionally, the memoization table stores results for all possible states, and as we derived earlier, this contributes O(n*(m) to the space complexity. Therefore, these two components together form the primary contributors to the space requirements. Another factor influencing space complexity is the recursive call stack. The maximum depth of recursion corresponds to the length of the strings S1 and S2, which is n. Each recursive call uses a constant amount of space, so the call stack adds O(n) to the total space complexity. When we combine the space used for the KMP preprocessing, the memoization table, and the recursive call stack, the overall space complexity remains O(n*(m). Now, let's compare this optimized approach to a brute force solution. In a naive approach, we would generate all strings between S1 and S2 and check each one for the presence of the evil substring. Since the number of strings in the range grows exponentially, this results in a time complexity of O(26 to the power of n*(n). Clearly, the optimized algorithm, with its O(n*(m) time complexity, is vastly more efficient. The optimized solution also outperforms the brute force approach in terms of space efficiency. A naive solution would require storing all possible strings in the range, which leads to exponential space usage. In contrast, our optimized approach uses a memoization table and a call stack, resulting in a space complexity of O(n*(m). Another useful perspective is analyzing the best and worst case scenarios. In the best case, if the evil substring is empty, meaning m equals 0, the algorithm simplifies significantly because no matches need to be tracked. This reduces the complexity to O(n). In the worst case, when m is large and the range of strings spans the entire alphabet, the algorithm still efficiently computes state transitions using memoization, maintaining the complexity at O(n*(m). To confirm the derived time complexity mathematically, consider that the memoization table has O(n*(m) states. For each state, the recursive function loops over the alphabet, adding a constant factor of 26. This results in a total time complexity of O(n*(m). The space complexity is dominated by the memoization table, which also scales as O(n*(m). These calculations align with our earlier analysis, confirming that the solution is both time and space efficient. This optimization ensures that the algorithm can handle even larger inputs effectively, making it a significant improvement over a brute force approach. When working on this problem, there are a few common mistakes to watch out for. First, overlooking edge cases can be a critical error. For example, failing to handle scenarios where either S1 or S2 are empty strings, or when the evil substring is not present in the range, can lead to runtime errors or incorrect outputs. Testing with edge cases such as S1 equals A, S2 equals Z, or evil equals ensures your solution is robust. Another common mistake is relying on inefficient brute force methods, such as generating every string between S1 and S2 and filtering them for the evil substring. This approach is computationally expensive and impractical for large ranges, often leading to time limit exceeded errors. Lastly, it's important to respect lexicographical order when working with strings. Unlike integers, strings follow specific ordering rules, and ignoring these can result in logic errors when comparing or generating strings. Another challenge is misunderstanding the problem's scope. For instance, confusing a substring with a subsequence or misinterpreting whether the range is inclusive can lead to incorrect solutions. It's crucial to carefully read and understand the problem's requirements to avoid this mistake. Additionally, hard-coding values, such as fixed string lengths or static checks for substrings, is another pitfall. Hard-coded solutions lack scalability and adaptability, making them unsuitable for diverse test cases. Instead, dynamic and flexible approaches are necessary to handle varying inputs effectively. These missteps are avoidable with a clear understanding of the problem and thoughtful implementation. To handle this problem efficiently, adopting a dynamic programming approach is often the best choice. Here, a common strategy is defining a state based on three factors: the current position in the string, the prefix match with the evil substring, and whether the current string is still bounded by S1 or S2. This allows us to count valid strings while avoiding those containing evil. When working with substring constraints like this, the Knuth-Morris-Pratt algorithm, KMP, is a valuable tool for optimizing prefix matching. In interviews, it's also important to communicate your thought process clearly. Discuss the trade-offs between brute force, backtracking, and dynamic programming approaches, highlighting why brute force is inefficient for large inputs and why dynamic programming excels. Be prepared to address edge cases, such as when S1 equals S2 or when the evil substring overlaps itself within a string. This problem shares similarities with other LeetCode challenges, which can be helpful for building your intuition. For example, LeetCode 139, word break, involves checking substrings under constraints, much like this problem. LeetCode 44, wildcard matching, focuses on string matching with additional rules, often tackled using dynamic programming. LeetCode 10, regular expression matching, requires pattern matching in strings, another problem well-suited to dynamic programming solutions. Lastly, LeetCode 940, distinct subsequences 2, involves counting subsequences under constraints, which parallels the idea of counting valid strings here. Exploring these problems can deepen your understanding of related techniques and strategies. There are alternative approaches to solving this problem, each with its own trade-offs. Backtracking is one option, where you generate strings recursively while pruning paths that contain the evil substring early. While this method is simpler to implement, it becomes slow and inefficient for larger input ranges. Another approach is dynamic programming combined with the KMP algorithm. By pre-computing prefix matches for the evil substring using KMP, you can design a dynamic programming solution that is both efficient and scalable. However, this requires careful state management and implementation. A third option is an automata-based approach, where you construct a finite state machine for evil and traverse valid strings while avoiding the evil substring. This method is highly efficient but introduces additional complexity. Each approach has its strengths and weaknesses, so the choice depends on the context and requirements of the problem. Great work! Today, we tackled the problem Find All Good Strings, explored multiple approaches, and learned key optimization strategies. Remember, understanding constraints and time complexity is crucial for efficient coding. Thanks for joining, and don't forget to subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!